Alright, so this is like my 15th fucking time trying to do the Arenas one as well. And Arenas. I do not like these because they're like really useless, but you gotta know them because if you get asked a question about the hydronium content of something, you're gonna want to know that an Arrhenius acid, when placed into water, increases the concentration of hydronium. So that might be kind of confusing without an example. So let's draw one. I don't know, fuck, let's just do HCl. Because it's easy and lazy. It's gonna go with the water. That's gonna make hydronium. You're gonna have to kind of get used to the fact that when you have something that it's always gonna be called an acid. I mean, when you're doing an Arrhenius thing, because you know when these were named, they were named because they're acid. This is hydrochloric acid. So this is going to give this hydrogen to this water to make hydronium, and that is why we call it an acid, because when you put this in water, this it's hydrogen, but we call it a proton because all hydrogen is essentially just a proton with a little baby electron around it. But in this case, we're going to assume that it's just a proton, so it's actually H+, and that gets added onto the water, which is at this point neutral, but now it's going to be positive hydronium ion with negative chlorine. And the entire reason we do this is because it's just the simplest way of doing this, and it only works when you do water, is when you put this in water, you will always get an increased amount of this, because this thing will always bind to that. And that's really all you have to know for the Arrhenius acid. I mean, your professors might ask something along the lines of, and I mean, I really think this is stupid, because there's much better ways of talking about acids, but it's like the number one. There's the first step you're going to learn when you learn anything about acids, and it kind of confuses people because it's not necessarily useful. But so let's say you have, I don't know, CO2. I don't want to do water. CO2. O2, NaCl, and hydrofluoric acid. Now you probably assume that the hydrofluoric acid is going to be an acid, and you'd be right. But like I said, it's really stupid because anyway, I don't want to bitch. But so your professor might ask something along the lines of, you have these substances and you add them into water. Which one of these is going to be an Arrhenius acid? And it'll be a multiple choice question or something stupid. And your first thought is probably going to be this, because this is the only one that looks like an acid because it has hydrogen. Everything else doesn't have it. And they probably won't even give you one that has a hydrogen unless they want to be a dick. But you might have to prove that it's that, because the hydrogen, like I said, this is gonna ionize. Not all acids ionize completely, only the strong ones, but hydrofluoric is a strong one. So hydrogen plus F minus. This hydrogen has to go somewhere, so it's going to go in the water in the solution, and blah blah blah, and you're going to get H3O every time. Every time you put an acid in the water, you're going to get more H3O than you started out with. So that's really all you need to know. Alright, so the second definition of an acid is called the Bronsted-Lowry definition. Bronsted-Lowry acids are any species that donates a proton during a proton transfer reaction. And that's just a fancy way of saying that in this reaction, I'm just going to tell you right off the bat that this is an acid. And we can kind of tell it's an acid because we got to look at, okay, so this is clearly related to this. This is clearly related to this. The best way to figure out which one is the acid and which one is the base is if on one side it has more protons than on the other. So this has 4 protons right here. This one only has 3. This one has 3. But over here it has 2. So if it has more protons on one side, it's probably going to be more acidic, because it's more likely to give up a proton. So this is clearly the acid, this is the base. And just like the Arrhenius, whichever one is the acid on one side is always going to be the base on the other. So base and then acid. And that's really all you need to know for the Bronsted-Lowry. It's basically just a hydrogen being transferred over from one to another. I mean, I could color it in a different way. Or I could actually probably even draw this out. So, I have... This is going to be the hydrogen that we're going to be looking at. And that is attached to... I don't know if I'm drawing the Lewis structure right, but... a nitrogen. And that is going to be added to OH. And during this reaction, what you're going to end up getting is you're going to want to figure out this guy is going to be attached to here somehow to make this. So, there. So we have that. Let's just erase this and I'll draw the products. So that old... Alright, so I just ended up drawing this as a Lewis structure. So, I kind of drew it backwards though. So, water, NH4, NH3, hydronium. And I just drew this because it makes it easier for me to show you that this is a proton transfer that's going on. So we look at the 4 hydrogen over here, and I just made one of them green, you know, easy to see. This goes over here because the water has to gain this hydrogen from somewhere, so it gains it from here. That's how you know it's the acid. Alright, this is like my 18,000th fucking time trying to do this part of the video of the Lewis acid. Let's hope I get it right so I don't have to keep doing this, because people probably think I'm crazy in my house for saying the same thing over and over, but... Okay, so we have this reaction. We're going to just pretend that oxygen is part of some salt that when you add it to the water, because we're going to just pretend this is happening in the water, just because I am lazy and don't want to do this one anymore. And this is, let's say sodium was attached to it, so sodium's going to break off, so we don't even have to care about it, it's a spectator ion. And, well, I mean, it's going to be on this side too, but again, we don't care about it. So, let's go about figuring out what the hell this is talking about. So, Lewis acid is any substance which can form a covalent bond to another substance by accepting electron pairs. So, in order to understand what the hell that means, I have to draw out the Lewis structure for all of these things. So, for oxygen, and I'm going to cheat, I'm not going to do the dot model. I'm just going to do this. That adds 2. Alright, so, like I said, this is going to lead to SO4. So, I really hate drawing out Lewis structures. It's take forever. But we need to do it to understand this. So, in this reaction, like I said, we're trying to find the acid. So one of these is going to be the acid, one of these is going to be a base, and the acid is going to be the one that accepts an electron pair, so one of the little dashes over here. So, which one of these looks like he's going to accept the electron pairs? It's probably not going to be oxygen because he has 4 of them. You can't really fit a 5th one on there. But this guy only has these 3, so he's got an open area. So, and we also know that's going to be SO4. So we could assume that oxygen, because it's negative, is going to have all 4 of these. That's why I did this, because oxygen, not negative, would only have enough to fill 6 in its valence shell. So we could assume that it has all 8 of its valence electrons. But this guy doesn't, so I guess we could call him positive. +2. So he's going to want these electrons, so he's going to be the acid because he's going to be accepting this guy, and in doing so he's going to form a covalent bond with him by accepting these guys, and that completes his shell. His shell's already complete, and then you get this. And I finally fucking made this part of the video. Sweet.